Right, good morning, everybody. Thank you for taking your time to join us. We're a few minutes early before the start of the webinar, so please bear with us. We'll give people a couple of minutes to join in because people often finish exactly on the hour their meetings in their calendars and then have to jump across to these calls. So we might see a few people tripping in. So please forgive us for a few moments of silence while we allow a few more people to join, and then we'll get going properly on this webinar. Okay, time to start. Well, good morning or good afternoon, everybody. Thank you for giving us your time and coming to listen to our session here. This webinar is one of a series that we've done over time, and you can always go back to our YouTube channel or our website to find out more information about previous webinars and topics that we've covered. In today's webinar, you've got me. Hi, I'm Saul. I'm the Vice President of Sales at Synaptec, and my colleague Neil, who's our Chief Technology Officer. Dr. Neil Gordon will be taking through part of this. We wanted to catch everybody up about technology. Before I do that, and we actually start this proper, a couple of housekeeping notes. Participants are on mute. You're probably very used to these kinds of Zoom tools these days, but you're on mute. Please use the Q&A channel if you've got questions that come up live during the program. We will endeavour to keep up with you and reply to questions as we go along, but sometimes it's not possible. And at the end, we'll allow a bit of time for Q&A, and we'll be trying to review the most popular questions and summarise them and talk about them, time permitting. However, if it does overrun or you've got very specific questions that you need to know a lot more about the content that we're providing you because it prompts thoughts about how it applies to you and your business, that's great. Please contact us afterwards, and everyone who's registered and then who's attended this event will of course get a copy of the slides, so don't feverishly write notes. We've got plenty of material here. We'll give you a recording afterwards so you can review it and get in touch with us afterwards. So I think that's everything for the housekeeping questions, and that fortunately gives us a few minutes of time for people who are still joining and totting up on the call. But let me start this properly. So the theme that we wanted to come up with today for you was about how our technology helps with advancing grid resilience. And the way we're going to do this is to talk to you about this in kind of three segments. We need to explain a little bit about what the underlying platform technology is and how we put together that technology, how that turns into products and then services and benefits for customers. So Neil's going to take you through a lot of this stuff, which is about how it works and how it operates and why this is different from conventional monitoring techniques. And then having done that, so that there's a kind of a baseline established of understanding of how the technology works, we'll go into the solutions, which is much more about some real world examples of how we've deployed it recently, what customer insights have been gained from it, and what potential there is for operational cost savings operating these high voltage networks that we're monitoring. So hopefully you'll find some of these interesting. It's not an exhausting list of everything we've done. Not an exhaustive list of everything we've done. It's simply some recent and very interesting examples that will be indicative of what's possible, and it might just help at least with your understanding and knowledge, and maybe help address some problems that are plaguing you as you're trying to manage operations on your power systems at the moment. So with that said, Neil, I'm going to hand over to you to get into the first segment where we explain the solutions, products, and platform technology that's underpinning everything, please.
Perfect. Yeah, thank you, Saul. And yeah, hello to everyone. So as Saul said, I just want to take a moment up front to explain how we kind of stratify Synaptec's offering. And then what we'll do is we'll talk you through each component. So I'll talk through the platform and the products and then hand over to Saul to talk you through a couple of specific solution examples. So, as I've said, really already, we've separated the kind of offering at Synaptec into the platform, the products that are built upon that platform, and the solutions that those products enable that address real power networks problems. So, to begin with, the platform is our patent protected unique fiber optic measurement technology, which we call distributed electrical sensing, or DES. From that platform, we build discrete products, which are the sensors themselves, the interrogation systems which monitor those sensors, and the analytics modules. These are the individually certified and type tested building blocks, which then become solutions. So the solutions are therefore the configured combinations of those products, which address those specific industry challenges. And the two solutions that Saul is going to talk to you about later on today, once you've got a good understanding of the kind of underlying technology, are mixed circuit protection, a kind of protection enhancement product for mixed circuits, and Greenlight, which is our cable condition monitoring platform. So first, just to explain how the underlying technology works. So what is this thing that we call distributed electrical sensing? So DES is Synaptec's unique precision measurement technology. Very briefly, what this technology lets us do is deploy passive point sensors for current, for voltage, and for temperature over very wide areas on power networks using the existing single mode optical fiber network. This enables many protection and monitoring applications for operators that without a technology like this would be hugely expensive to deliver, basically. The technology is very quick to install because it requires, as you'll see in a moment, no supporting infrastructure at each measurement location. The sensors are passive, so they don't require digital telecoms or power supplies or GPS access at the measurement location. It operates over extremely long distances, further as standard than any other power networks monitoring approach. As I've said, it's passive and it's stable year round under different weather conditions. It's inherently cyber secure because of the methods that we use. And really, most importantly of all, it's tried and tested by operators in the field and has been for several years. So it's been deployed for several years now with operators in the UK, in Europe, in the Gulf states, in India, and across terrestrial T&D applications as well as offshore wind. So that's kind of an introduction to the technology, and now we're going to look a bit deeper at how it works. So it allows measurements of current and voltage and temperature to be deployed over distance, but yeah, how does that really work? So what we do is we leverage the existing single mode fiber that is installed in most modern power networks alongside cables or in the OPGW, the optical ground wire on the overhead line, and we use that to install our sensors at these remote locations. So as you can see from this little cartoon here, we can reach out over a wide area throughout different parts of the network infrastructure and install these sensors for measurement of voltage or current or temperature in series along that fiber. So any one of these sensors could be any one of those different measure ends. You have no auxiliary power at each one of these locations. So there's no power supply, no digital telecoms, no local time sync, no expensive civil works to deploy. So they're extremely quick and simple to install while also crucially maintaining compliance with critical measurement accuracy standards. The electrical sensors themselves, which I'll come to in a bit more detail later, they interface with the secondaries of standard instrument transformers, CTs and VTs, to allow us to access the primary current or the primary voltage in that circuit. So you can really think of this technology on the electrical measurement side as allowing you to use the same reliable, trusted, simple transformers that have been used for decades in power networks in new locations, okay, in remote, hard to reach locations. So we have all those sensors installed throughout the network, and then at a central location, usually in a substation, we have our interrogators. And what those do is they receive the measurement data from all the sensors in that fiber array, and then they digitize it, they locally synchronize all those measurements, and they output measurement data. They perform analytic functions for long-term trends and condition monitoring, and they perform rapid onboard functions to enable things like protection applications or protection enhancement applications. So that's kind of broadly what this scheme looks like, but what's really unique about it? So the first important thing to say is that DES, distributed electrical sensing, is not just another optical CT or NCIT, which I'm sure you'll all have heard of and which have been offered by a range of manufacturers over the last couple of decades and have kind of not really succeeded in taking off to any great extent. So we are not that type of optical measurement. As I've mentioned, what our method does is it passively instruments the secondary of standard instrument transformers, allowing you to install those in new locations. So we use a fundamentally different physics to OCTs or NCITs. We don't require any of the complex specialized fiber wrapping technique that you would have to perform to install those in a new location. And we know those techniques are susceptible to error creeping into the measurement because of poor winding and poor installation. So we do not use that technology. We can reach unprecedented distances, so up to 60 kilometers on a single fiber between the interrogator and the last sensor in the array. And we can reach further by integrating optical amplifiers if that's required. Our measurement technique is inherently immune to electromagnetic interference. Again, unlike OCTs and NCITs, which are polarimetric measurements which are susceptible to interference. And what that means for us is that you receive exactly the same measurement that you took of your CT 60 kilometers away at the substation. It's not changed over that transmission period. And crucially, our methods are protected by a strong patent family. And there's one in particular that I just want to flag, which protects our method of time stamping those measurements which are taken over that very wide area. So any system that deploys passive optical sensors over fiber, be that DES or OCTs or NCITs, will naturally incur a time delay as the light traverses that fiber over tens of kilometers. What our patent does is it accurately corrects for that time delay. Now, this patent is generic. It doesn't just apply to DES. It applies to any passive fiber optic measurement technology. And what it does is it guarantees our measurement accuracy and our compliance with industry standard communications protocols over long distances. So Synaptec can guarantee that a measurement taken with our system at 10 kilometers, at 20 kilometers, at 50 kilometers from the substation has exactly the same timestamp accuracy, phase accuracy, and communications protocol compliance as if it were taken right next to you in the substation. And that's unique to us. To our knowledge, no other method exists other than using our patent to achieve that performance. What that means is that any other optical sensing technology will incur a significant and increasing timestamp error the further away sensors are installed on the fiber, meaning that accuracy standards and protocol compliance cannot be guaranteed. Now, this is Synaptec's patent, and we do not license that to any third party, so it's unique to the DES platform. So, kind of this little graphic just summarizes applications. So I'm not going to go into this in too much detail because Saul will come to these later on. But in brief, then, DES is a high-performance measurement technology for power networks applications, and it enables many of these kind of protection enhancement, and long-term condition monitoring applications. So built off that high-performance platform, we then have our discrete products, which, as I've said, are the discrete and type-tested components which build those applications for customers. So what are those key building blocks? Well, they're all listed here. There's quite a lot here, so let me just get this laser pointer so you can see what I'm talking about. So on the right-hand side here, you've really got the DES sensors. So starting from the right, you've got our passive temperature transducer, which is a small point temperature sensor often deployed to measure temperatures on assets like cable joints and terminations, or any other critical items of plant. So this example here is about 2 or 3 centimeters long. It's a small patch that gets applied to any item of plant that you want to measure the temperature of. Our electrical sensors for current and voltage are captured by these devices called passive secondary converters, literally because they are passive at the measurement location. They have no active electronics, require no power supply, and they convert the secondary of a standard instrument transformer into an optical measurement. These come in 2 flavors. I'll come to these in a bit more detail on the next slide, but you have the PSC1, which is our ruggedized remote outdoor single-phase measurement, and the PSC3, which is designed as a 3-phase measurement unit to deploy in the substation in the protection and control rack, for instance, and really is typically used to retrofit to the secondaries of an existing CT in the substation yard, so you don't have to install new CTs at that location. Beyond the sensors, then, we have the interrogators, which monitor centrally all of the sensor arrays over optical fiber, and they generate measurement data, typically in IEC 61850 sample values, and they perform rapid onboard functions, for instance, 87L protection, differential protection algorithms, to enable those protection scheme enhancements that Sol will take you through. Now, these interrogators, I should say as well, are also type tested to the same level of rigor as a protection relay or another equivalent IED in the substation. So they've been through a rigorous amount of testing for that environment. Then we have Synaptec's analytics systems, which enable long-term data logging, visualizations, and analytics on the large volumes of data that are generated from our arrays of sensors and from the interrogators. And finally, we also integrate additional third-party systems like DAS and DTS, which complement our technology and provide things like integrated temperature, strain, and acoustic event monitoring throughout the fiber network, and enable more complex analytic functions in combination with DES, like real-time thermal rating, RTTR, and other things like that. So let me just move on to telling you a little bit more about PSCs, because this is where we want to be really clear about how it works and how it installs. So I've already mentioned that these come in these two different flavors. The one you can see on the screen here is the PSC1, which is our IP68 rated ruggedized outdoor version for installing well beyond the substation fence in a remote or challenging environment. We also have the PSC3, which is on the bottom of this slide here, which is just the rack mount version. But fundamentally, they're doing an identical function. They're converting the secondary of the CT or VT that's connected to it into an optical measurement. And they're doing that without any local power supply, without any local time synchronization signal, and with no digital telecoms access. Just to stress again, this is nothing like an optical CT. So we require no complex fiber wrap, which is susceptible to error. We have no sensitivity to electromagnetic interference, and we're stable over environmental temperature extremes. So this method really then allows the deployment of tried and tested CTs and VTs in new locations over very wide areas without the extreme costs of deploying a new substation to support that infrastructure. You can actually think of this system of interrogators and PSCs together as like a very, very large merging unit that operates over very large geographical areas, because we're digitizing the secondary of a CT and making that measurement available in a substation, which could be tens of kilometers away. Now, in terms of installation of these devices, it's very, very straightforward and quick. So a CT, for example, can be deployed at a cable ceiling end. Say you want to do a mixed circuit protection application, like Sol will come to in a moment. There you want to install your CT around the insulated cable, mount your PSC nearby, and make the electrical connection to the CT. And then the optical fiber connects in series through all of the sensors in the array. So each PSC at a given location will splice into the existing optical fiber coming down from the OPGW into the cable, for instance, at any convenient local access point. So at a fiber optic splice box, which is typically nearby. And that splicing operation on single mode fiber is a bog standard telecoms operation. It's very quick and simple for a telecoms engineer to do. It takes moments, a few seconds really. So each PSC is installed in series down that fiber. They're daisy chained down the entire length of our sensor array. And the full PSC suite of products is also type tested to IEC 61869 and the various EMC vibration environmental requirements, just like any other measurement technology in the sector. So hopefully that's given you a kind of whistle-stop tour of the technology. Obviously, if you have questions, please put them into the Q&A and I'll come back to them at the end. But at this point, I'll hand back to Sol, who can then take you from the platform which underpins the products that I've just taken you through, and then how those are built into solutions which solve real problems for the industry.
All right, thank you, Neil. So with that concept in mind, we'll show you how it's applied here in two steps. We wanted to talk about the challenge of protecting complex circuits like mixed circuits that combine overhead and underground cable sections, which is increasingly prevalent in a lot of high voltage and medium voltage grids around the world. And this is all about ensuring that you never reclose on a cable section fault, which causes a lot of damage and increase the cost of an outage at very least. In the second part of my session, I'll also talk about not how this technology responds post-event to a fault, but also how we try to prevent them, because of course prevention is ultimately better than cure, and this technology can be used as effectively as a very early warning system to give operators notification that a fault is coming, so you've got time to plan an intervention and avoid it in the first place. So with those two thoughts in mind, we'll try and translate Neil's sort of theoretical view of how it works into how it actually gets deployed. Now, I started talking about mixed circuits. This is probably the most popular product that we sell. I think we sell more of this than anything else. And I think everyone in the world probably knows why. Everyone has slightly different reasons for this, but more and more circuits are being undergrounded around the world, either to avoid new civil infrastructure growth or to avoid extreme weather events, which are only presumably going to get worse through our lives. Sometimes it's about avoiding places of natural or outstanding beauty, and you just don't want the towers and lines going across a lovely picturesque landscape. Sometimes it's about congestion capacity, or indeed integrating renewables and critical loads. Whatever the reason is, I think everyone knows there's an amazing amount of cable production and installation work going on around the world. And from a protection perspective in the grid, cable sections within a circuit present a unique challenge, because sometimes these cable dips, these cable sections, could be quite far away from the substation, and that monitoring location could be very remote or inaccessible. And maybe there's no substation there, maybe there's no access to telecoms, maybe there's difficulties obtaining power supplies. So it's very difficult to reach very far out of the substation. If you think of Neil's presentation, what we're effectively saying is you've got information about assets inside the substation as if they were in the yard, but we're reaching out past the fence and going very far away to these remote and inaccessible locations to give you that instantaneous visibility and control of what's happening out there. So sometimes the location, like a transition point of an overhead line going to a cable section, it's simply too far away, or it's too inaccessible, or it would cost way too much money to build a substation and then the dedicated secure telecoms to knit the information back to the center to compare currents and understand where the fault is. So protection policies and protection budgets don't easily align on this one. And it's true to say that the policy itself doesn't completely work. Very often when we talk to our customers, we find either their policy is never to auto reclose if there are cable sections in the circuit, because that, if it always auto recloses, you risk accidentally reclosing on a cable section fault. That's a permanent fault. That's going to be very expensive and cause a lot of damage, because you're exposing assets a second time when you reclose to fault level currents. Or you're always reclosing. Either way, there is a challenge here, because it's a suboptimal solution. The perfect solution would be that you can distinguish between transient faults, maybe a lightning strike or vegetation brushing against the line, something that goes away again once it occurs, and then you can restore power safely. You want to have that ability for overhead line sections, which are always transient faults, and discreetly and separately understand if the fault was in the cable section. And when you do that, you can avoid or stop proactively the reclose command, so you never accidentally reclose on the fault in the cable section. So the idea is to distinguish and differentiate where the fault is, whether it's overhead or underground, and then slightly change the post-event response so you get a more targeted and granular response to the fault. Now, our technology is very good for doing this because, as Neil said, you can reach out from the substation over long distances. We recently deployed a system which goes up to and even fractionally beyond our maximum quoted range of 60 kilometers, so that you can install sensors and create protected sections far away from the substation, but monitor them centrally. So you've got this idea of reach and distance, a lot of scalability and range that's possible. It's very safe and easy to install, as Neil's already covered, because it's standards compliant. And when Neil says it's cyber secure, well, there is literally no data outside the substation. There's just light going up forwards and backwards through the fiber. It's completely unhackable and unbreakable. You'll only create data at the center by those super merging units that Neil described, the interrogators. So this is a very simple way that we've developed with some leading operators to deliver that centralized protection and control function. And most mixed circuits would look something like this. Back in the substation, you've got our interrogator probably living in the relay room in the protection and control rack, and it's reaching out along the fiber outside the fence, maybe running 10, 20, 30, 40 kilometers away, and suddenly there's a cable section in the circuit. What we can do is install 3 current sensors at the first transition point, nearest, if you will, and another 3 current sensors at the furthest point away. And then by measuring those 6 currents, we're able to create a protected section. And all of that information is continuously, permanently, and synchronously made available by the interrogator to the protection scheme in the substation. What we're simply doing is signposting or informing the protection scheme where the fault is if it occurs. And in fact, we've had an example recently where we helped an operator manage a fault correctly with the system installed, where you've got an overhead fault, and we've said, good, if the fault's in the overhead section, you can reclose. If the fault's in the cable section, we'll tell it straight away, and we'll see it within milliseconds from the differential currents that are measured centrally, and we can say, no, for sure, and in protection timescales, yes, that fault is in the cable section, so we're going to recommend that you block the auto reclose and don't reclose on that fault, right? So this has a significant cost saving and an outage saving. It's the right way to think about it. We're just deploying the logic of line differential protection to create a multi-zone protection response and improve how the protection scheme responds to a fault by being more specific about where it's occurring and changing the response according to where that happened. Now, this actually is a pretty typical circuit that we've seen, and you can see a picture of the sensors on the transition tower there. So right at the cable ceiling end, as the line comes down and the cable comes up, it's probably about 10 meters in the air, we're grabbing those 3 phases, measuring them, and then looping the fiber back into the fiber array so it continues to the far end. But it means everything, all of the sensors are always visible to the interrogator at the center. And then the interrogator has a simple choice. Depending on whether you're ready to adopt 61850 and process bus and station bus or not, we can either manage to inform the protection scheme using dry contact, or we can use basic 61850-9-2 sample values or 61850 goose. So all of our interrogators are ready to deploy now on conventional schemes. But if you're ready to go to 61850 or you're thinking of going digital soon, the interrogator's already ready to do that. It's in 61850 is built in. Okay, so it's future proof. And fundamentally, it means you'll have millisecond timescale and very reliable and robust response to faults, no matter how far away they are. In the case that I just mentioned to you, where one of our sensors is 60 kilometers away from the interrogator, you'll still see that fault and we'll still be able to receive that information, process it, timestamp it, and publish it all within milliseconds before the breaker even operates. The system will know if it's safe to reclose. We're talking like 9 to 10 milliseconds is a typical operation time here. So that's a very simple conceptual view of mixed circuit protection. Now, in the real world, you might have multiple cable sections, or you might have them in series or in parallel. So there are many different examples of this. And just to give you a few of our more recent ones, with some transmission and distribution operators around the world, we just grabbed a few images and logos here to give you a sense of how it's used, because topologies do change. And sometimes you have to, as Neil said, design a solution with all of our product components that meets the requirements of the topology, which might be unusual. So we've had examples where we've had a circuit running across a series of like mountains and lakes. And so you've got several dips, one after the other, and you have to manage it like that. Or you've got examples of cable systems in the middle of the desert where there is no access to power supplies. You can't build a substation out there, and there's no way to link the communications back. There's simply no communications infrastructure to take use of. So most of these examples are situations where the circuit is traversing challenging domains and geographies where it's very difficult to install conventional systems out there, and so the operator simply didn't. And if they make that choice, that's okay, but clearly you're taking a risk because the protection scheme might not operate properly if the fault's in the cable section. So this system delivers that reassurance and rapid response in a scenario where you've got that remoteness or the inaccessibility, you can't have access to telecoms at that location, or you simply don't want the cost of building another another substation to host all of that infrastructure. I think these are all sort of interesting ideas. And again, if anyone wants to see some even more detailed examples of how this deploys or how this works, we can't show you it here because it's frankly not a very exciting thing to see on a slide, but in our labs in Glasgow at our headquarters, we often invite our customers along to attend the lab, and we can simply set up a system to emulate a circuit and show some of these situations where we can throw a fault and you can see the response times and how it generates reports, how it records those events for post-event analysis. But the critical thing here is to have that confidence in a robust IEC compliant protection enhancement system that's taking away any risk of damage caused by reclosing on cable faults. That's really the cool thing. So some interesting examples there that we can talk in more detail in afterwards if anyone's interested. But the summary of this thing is you can now deploy a multi-zone protection scheme without the traditional cost of the secure, dedicated telecommunications and data networking infrastructure, or all the substations that were traditionally needed at all the different points. So there's a fundamental reduction in the capital cost of instrumenting these systems. At an operational day-to-day level, clearly there's a saving because depending on where you started in your policy, you're either not running around looking for where the fault is and losing time that way, or you're able to avoid exposing cables and surrounding HV assets to that fault level current a second time and causing a lot of damage by reclosing incorrectly on a permanent fault. So if you've got that sense of discrete auto reclose, and yet you can do it without the traditional cost of control power, data networks, and substation work and civil works, there's a big saving at a CapEx and an OpEx level. Clearly, that's also a risk reduction. It's also an outage reduction that comes through in your SAIDI and SAIFI numbers, which are critical. And it's a simple thing now to do and to deploy for a sensible cost that gives you that implementation of best protection practice in reality. So it really is about avoiding damage and restoration of power rapidly and safely. Maybe familiar to you, but for a lot of our customers don't know that this is actually possible, and it's still a surprise to some people. So we do these webinars just to educate and make people aware that this is a viable solution that's already been deployed for many years in the field at various voltage levels and distances. So that whole section is about how we avoid closing on permanent faults. The other part of this is, well, that's after the fact. Is there a way to manage cable systems? They could be underground, they could be underwater. Is there a managed way to monitor them and catch an early warning sign of problems so that you're notified in advance of the fault that something's going to go wrong? Because if you get enough time to respond, you can plan an intervention and avoid the failure, which would be even better, right? And that is something we also do, and the product solution is called Greenlight. And so this is about reducing the fundamental risk of operating cables in extreme environments. Perhaps it's subsea or underwater or under the city, you haven't got access to it. It's hard to go and inspect and check these things. This is about lowering the lifetime operating cost of that asset. And we'll show you how it deploys in these scenarios. Now, I'm covering a wide base here, so I appreciate there'll be different people with different kinds of networks trying to understand how this deploys for you, but it has been used in offshore wind, in subsea cables. It's been used underground and under bodies of water and under cities. The message here is that whatever kind of operator you are, I'm sure you recognize that there are challenges inherent with deploying cables. Not only are they much more expensive to install than overhead lines, but once they're down there, it's really hard to see things going wrong, and it could be dangerous to conduct regular manual inspections and visits to ensure they're okay. Scheduled maintenance costs are high, and in some cases, we've seen some truly shocking numbers involved in the cost of cable failures. The most extreme event you can see here that was actually published in the UK that came from an offshore wind failure was an outage cost that went to 80 million pounds or $100 million. That's an extreme case, but it happens. What we've discovered is that when people are planning to use cables, the conventional approach to risk analysis and mitigation is to consider things like DTS or online, not offline, but online partial discharge monitoring. Now, when that's done, there are still some risks left unmitigated, and fundamentally, what it boils down to is that the cables themselves, the structural integrity of the XLP of the cables is actually normally okay. Maybe that's 1 in 3 or one in in fact, 30% of failures would be about right. 30 to 40% of failures are in the cables themselves. It's the joints and terminations where most of the failures are happening. And I've seen published data saying that's about 57% of all failures that have been analyzed in recent DNV reports. But whenever I speak to customers and operators, they always tell me, no, it's much higher. We've heard 70 or 80% in different cases. So the majority of the failure is happening where a human was involved, either terminating or connecting that cable. It's the link boxes, the joints and the terminations where you have the problems. It's not the cable itself. And unfortunately, all of the conventional instrumentation, like distributed temperature sensing or DAS, that's looking at the structural integrity of the cable, so it misses the joints and terminations. When you try to do manual inspections, sometimes you can't see at an electrical level what's going wrong, and it's a bit of a superficial task, and you don't actually get ahead of or identify problems as they're starting to occur. So there's a challenge and a limitation with conventional monitoring that says we're either looking in the wrong place, or we're not seeing it early enough, or the results are ambiguous. And often that happens, particularly on the generation side, with large inverters, that online PD signals are completely overwhelmed by the high frequency electrical noise generated by things like solar panels and wind turbine generators, such that you can't really detect it, and it's not absolutely clear if this is a problem or not. And so the noise factor, the attenuation, the interpretation issues make it quite a subjective and expensive thing to deploy. What operators asked us for was something more simple, a traffic light system that's either a red light or a green light. I'm okay to keep going, or I need to stop and there's a problem. So the idea here is to give the operator much higher confidence that there's going to be a problem to justify an intervention to go and check. So that's what we do. This chart I'll leave behind, but if I pick one out that I mentioned at the start here, was probably the most famous sort of poster child for cable failures, up to 80 million pound exposure. And interestingly enough, if you look at this chart, of all the recent ones that we spotted here in the UK, we're based in the UK, so of course I'm biased when I look at my numbers, whether it's underground or subsea cables, all of them were costing millions to fix, and all of them could have been seen in advance if green light were deployed on that circuit by looking at a combination of what's happening with phase current and its relationship to screen current, and also its relationship to the point temperature measurements of the terminations. If you know those correlations and you can see deviations and exceptions in those correlations over time, those are the best early warning indicators of something going wrong. So having said that, yes, we can deploy this technology in difficult, inaccessible places. All of these faults are traced back to issues that we could have seen and addressed with our technology and given not hours and minutes of warning, but weeks and months of warning. So you've got time to really schedule an intervention and ensure that you've dialed out that problem. But let's show you something real, because that'll be more helpful once we've explained a little bit about the structure here. Now, Neil touched on this before, but imagine there's sort of three layers to this solution. So Greenlight has all of the sensors that you can see on the top right there attaching themselves. You can see a CT being wrapped around a phase conductor cable, and to the extreme right you can see some Fistra style T-boot connectors with the temperature sensors mounted on the top of the T-boot, where we know we've got the best position for catching information about the temperature of the core inside. But all of those sensors are in an array spread out over a wide area, under a city, under a lake or a river, or perhaps out in the ocean. And all of the electrical sensors, and indeed DTS and DAS information, is all brought back to a central point. So you've typically got a cabinet at a central location where we're building up that data history of information about what's happening with that asset over time. And again, permanent, synchronous monitoring of all of those measurands. And that's the clue. At that point, we can serve up data. And some customers have said, just please give me the data. I know how to absorb that data into SCADA and make sense of it. But actually, there's so much data and there's so many correlations that we're looking for. It's normally much more helpful if we provide the additional service level on top of the hardware systems that says, we're going to help you see it, visualize it, interpret it, and check for things. We're going to automate all the event notifications and alarms for you, because we've pre-programmed the system with all of the typical and common failure modes that can be seen in a cable system. And then sometimes there's even a full service option where we help the customer. In fact, we always help the customer in the first time they deploy this to interpret the reports and insights and understand how to read through those notifications and pick out the ones that are really critically important and highest priority for action. So you've got this idea of sensors out in the wild at a central point, bringing together all that information synchronously so that you can start comparing things. And then either we automate what it means for you and tell you when there's a problem, or we actually help you interpret with, like, every quarter we have a running meeting with our customers who subscribe to this service, and we take them through the data so they can understand what they're looking for and train themselves for the future if they wish to do that themselves. But those are the three levels. Now, when we deployed this on, for example, one of the world's largest offshore wind farms, and we're looking at thousands of sensors and hundreds of cables operating over 25, or I think it's 30 years of operational life, the investment consideration is significant, because we are fundamentally de-risking that wind farm operation, and they know that they'll have cable failures over the lifetime of that array. And when you calculate how many there are likely to be, maybe 10, maybe 15 is a reasonable number in offshore wind, even today, with all of the focus that's been put into installing them correctly and trenching them correctly and operating them correctly. There are still a lot of unplanned, unscheduled failures. If you can avoid even the first one of those, let's say 10 failures, the system will pay for itself. And then over the lifetime of the array, remember, these sensors never need to be replaced, recalibrated, maintained, or updated, or have components changed out inside. They will operate that entire life untouched. Once you fit them, you forget them, they will operate. You've got this idea that across the entire operating life of a project, you're going to avoid several outage events. So the return is immediate. You get your payback if you save one fault, but if you save maybe even 1/3 or even 40% of the potential failures that were expected in the risk analysis, you're likely to get something like a 20x return on investment here, because you're avoiding not all of the failures, but if you avoid, a third of them, you'll make your money back, and you'll make a significant saving on optimized scheduled maintenance. That's the idea of saying you don't need every couple of months to go and check every one of these locations manually. We've inspected it for you, and you don't need to visit if it's running okay. And you've got that ability to reduce the cost and the frequency of visits. Now, if I say that another way, We often talk to our customers about savings across 4 different time periods through the life of a cable project, because you will ideally always test the cable during commissioning to ensure there are no latent defects coming from bad handling or manufacturing errors. But even testing is not 100% perfect. And what would be ideal is that you run a test, and immediately afterwards, when you've energized the cable, then green light is immediately working and noticing instantaneously if there's a problem. And we'll see that, for example, if we're looking at I'm making up a number now, 100 cables, and 99 of them the same, and one of them shows a very high or elevated screen current ratio as compared to the phase current. That would mean that termination work wasn't done correctly, and you can still get your contractor, who is probably still on site, to come back and fix that problem and re-terminate. So there's an installation quality assurance benefit of having green light available the moment you energize that circuit, because it's like a quality control. You're making sure it was installed properly and that what actually happens under load is what you expected. Having said that, there are obviously those automated notifications to avoid outage, and that could happen at any time through the life of an event. There are just random events where this happens. 10 years down the line, suddenly there could be a failure and everyone is surprised. But we don't ever talk about selling this technology and delivering it to customers on the basis that it'll fix or avoid these future failures alone, because failures in the future are unlikely and a long way away in the future. People tend not to think about risks like that because it's like, hey, that'll never happen to me, it's far away. But while it can help with that day to day, it's about optimizing scheduled maintenance and allowing you to redeploy expensive engineers to go and do more useful things for your business, because there are fewer scheduled inspections to make. I'll show you an example of one that's happening right now in a moment. And then, of course, later on in life, it would be very useful to know that as you're approaching the end of the operating life of the cable, and in some regions and in some countries, the regulator is defining this as like end of life. You've got to notify everyone like 5 to 6 years before end of life that this cable's coming to end of life, and you've got to make a decision about, are you going to replace it? Are you going to repower? And so aging characterization through the life becomes useful. And if you're always watching the cable and you're always able to run a calculation that gives you a health index and an aging effect score, you know towards the end of the life what state your asset it is and what it's worth. And you can make more informed end of life decisions as an asset management function based on data rather than offline spreadsheet based projections, which are probably less reliable, because you've got this data history building and building, showing how that asset is trending towards its end of life. Is it on schedule or better than or worse than what you intended? You'll know. So this is about informing decisions and giving confidence that you can see problems happening. And then, of course, optimization of capacity. This is not true for everyone, but there are occasions where you need to overrate cables and deliver more power at a certain time for short periods of time. And we've noticed that dynamic rating is incomplete without this technology. We'll show an example of why. And so sometimes when people specify DTS alone for what they call real-time thermal rating or dynamic rating, it's actually not enough. And we'll give you an example of that in a moment. So just moving rapidly forward, let's show you a really easy one. This is an example of a fistula connection where the incorrect torque was applied and there was a defect on the contact rod such that it developed a hotspot. And this graph basically says to you that if you try to watch this cable system with DTS, DTS cannot see this location and completely missed that spike that you can see here where the hotspot is developing, and you've got this sudden up ramp in temperature. So we were able to put a temperature sensor on the outside, and then there's an algorithm to calculate and infer what the internal core temperature was of the conductor, and we were able to give a very high accuracy early failure warning before you have a thermal runaway and it's too late to do anything about the damage. Similarly, deployed on a real high voltage system, what you're looking at here is a track of the cable system temperatures running through the summer in the North Sea in the UK. Now, we've mentioned before that DTS, whilst very useful for monitoring the structural integrity of a cable, like finding cold spots for water ingress or hot spots for excess burial, one of the problems with DTS is that you really need to understand what the temperature is at the terminations and joints. And in the middle of this chart here, you'll see this yellow schedule where we've got this increased temperature. Basically, what we noticed through the summer is that this cable was operating under sea, and the temperature of the cable itself was consistent, but the terminations were not underwater, they were up above the sea level in open air. And in the summer, they got very hot. And in fact, it was much hotter than the cable itself. In other words, the thermal limitation or ceiling of the system wasn't the cable, it was the termination. And if you can't see that termination with DTS, you don't know that's the weak point thermally where you've got a limitation, and you need to know what it is. So by applying our systems to contribute to the visibility of the hole, we've combined the DTS feed, which we supply the DTS boxes and the DTS information, and then you add the point temperature sensing on the terminations, and you can see that they were actually the thermal bottleneck. They were the limit. The cable was fine. It was the above air in the sunshine, getting very hot points that were actually causing the potential problem. So if you wanted to dynamically rate the cables, and if you wanted some kind of RTTR, DTS alone isn't enough. You need to understand the whole system comprehensively, and this is a great way to catch that. And perhaps finally, and most interestingly, a very recent example, but I think it's very interesting. Here you've got some pictures from our Greenlight software showing an emerging issue in a high voltage tunnel system of cables. Now, the challenge here was that the operator would like to have a policy that says, if I can see that my screen currents are significantly elevated in one place, let's say I'd like a screen current level of about 3-4% of phase current, then if it's suddenly much higher than that and it's suddenly gone to 6, 7, 8, 9, 10%, I'd really like to be informed of that, because that's a very clear indicator of a problem at that point, and I've got time to fix it before it fails. I can re-terminate, I can replace some parts, maybe there's a broken path, maybe there's a bad connection, some water ingress. There could be several failures associated with this. But traditionally, it's too expensive to put all the equipment, even partial discharge monitoring, in all of these locations. And in fact, in this example, in a 400 kV double circuit cable system with, I think it was 192 locations, that cost became prohibitive. So we were able to instrument all of those joint bays, each individual phase. So what is the phase current? What is the screen current? What's the relationship between the two of them? And have we got deviations? And very often it's the rate of change, or the amount of the rapidity or the amount of deviation that matters. It's not the absolute measurement, it's the change in the relationship. So if you've got a situation like this, where we actually saw a significant increase up to 8% in one place, that's one cable bay on one circuit and one phase of one circuit in one cable bay. We're able to pick up, it's that one, that looks wrong. It's not a disaster, it's not critical, it's not going to explode tomorrow, but it says to the customer, look, there's clearly two benefits I'm going to generate for you here. Number one, you've been notified what's going wrong and where, and you've got the time now and the confidence to plan an intervention and do something about it. Next time you visit, go and visit this one. The other benefit, of course, is, well, then you don't have to visit 100 other locations which are operating perfectly well. You can focus your time in that tunnel, accessing that point, to one place that needs attention. So you get that saving of the scheduled and regular maintenance cost. In other words, don't visit this location because it's Thursday, visit because we've seen something going wrong. Now, this approach is actually quite well documented, and those of you with access to the C-grade papers, or the B1 group reports there that I've put on the screen, actually is recommended by Red Eléctrica de España. So that's the transmission operator of Spain, that says, if I can see these screen currents, I can see the cable failures I'm really worried about that otherwise I can't see conventionally. And all we're doing is making that possible and giving you that real-time visibility and control and the ability to know exactly where to go and when to intervene. So again, much like our MCP system, the idea here is that you've got a technology which can reach somewhere really difficult to access, really far away, or maybe it's actually unsafe to go and visit regularly. We can deliver that live and instantaneous visibility and control without excessive capital cost, because again, no power, no telecoms, no data, but it's about reducing the operational risk and cost in the system operation, particularly for cables. And that's going to help and be expressed as savings in availability, safety, and of course, productivity. And again, just to re-emphasize, the whole point of this technology that we really want you to understand is it really does work with no power, no data networks, and no civil works. It does fundamentally mitigate risk because we're giving you advanced warnings so you've got time to avoid the cable going bang. And it's about avoiding those failures and those prolonged outage costs and repair campaign costs, which can be horrific. But day to day, even if that never happens, the system will help you to optimize scheduled maintenance cost and reduce that regular maintenance cost regime because we're able to identify what needs focus and attention rather than having to check everything. So with that in mind, hopefully we've just timed this to leave a few minutes left at the end of the presentation, but we hope this gives you an idea of how modern grids are obliged to use cables, but the cables can be better managed and operated and controlled by this sort of remote and passive sensing systems that allow you to avoid problems, or if there is a problem, to limit the outage cost and damage occurring. Now, I'll stop at that point because that's the end of the hour that we promised to take for you. Neil, I'm going to bring you back in and just ask a question. Yeah. Were there any particularly more popular questions that are worth repeating to the audience and saying, here's some of the answers to those popular questions?
Yeah, absolutely. There was quite a number of good questions came in. First one here, which we had a couple of inquiries about, was really about the limitations of the system. So what is it that limits us to a nominal distance of 60 kilometers and number of sensors per fiber? So I've given an answer to that in text, which people can see, but fundamentally that comes down to the optical loss in the fiber. Now, for simple systems, it's very easy to overcome optical loss in the fiber. As you get up to the tens of kilometers, typically how we address that is for a given circuit, we would have a survey performed of the optical fiber just to map out what the loss looks like in the system. And that's an incredibly quick job to do. It takes a few minutes really to take a measurement, and then we design our system to accommodate the amount of loss. Additionally, we can amplify if required to reach further or to increase the number of sensors. So the way to think about this is that at the solution level, we design a solution to meet the requirements of a particular circuit. So regardless of our limitations, we will be able to design a solution that meets your requirements. A second question, which came up, where there was a few kind of generally related to the operating environment, kind of the withstand. One question mentioned kind of coastal climates. So maybe the best way to tackle that is to say that the optical fiber that we use is rugged. It's designed with armoring on the fiber to protect the communications medium. The sensors are IP68 rated, and they've been installed everywhere from out in the desert in UAE to underground link boxes in Mumbai to mountaintops in Switzerland. So they're kind of designed for all weather, all environments, and offshore, of course, as well, as Saul mentioned. And there's a couple of open questions that have just come in. So one question, which you'll be anticipating, Saul, is asking about green light for online monitoring of HVDC. So, so all of our systems to date, just to cover that one off briefly, and then we might have to close then. All of our systems are AC at the moment. We are developing systems for DC, and I would say if you have particular DC monitoring requirements, we're particularly interested in finding trial partners and launch partners to help us test out our variants of these products for DC. So if you're interested to try and apply the benefits of this technology to DC networks, And we'd be delighted if you would get in touch with us directly because we'd be keen to use you as a kind of launch partner for that technology. So please do get in touch.
Great. Okay, thank you, Neil.
Probably have to leave it there, but there's a few other questions trickling in. I'll provide answers in text to those, and we can follow up with people afterwards.
So we've got a record of all the questions being asked, and if we failed to answer anything at all, or we were incomplete with our answers, we'll follow up with you. And again, to remind everyone of a few housekeeping notes just to wrap up today. So number one, thank you for giving us your precious time and listening in. I hope it was interesting and sparked some thoughts. We'd be happy to pursue those thoughts with you. Please get in touch with me and the team here in Glasgow, or we've got some partners and sales teams around the world who can help you. A recording of this has been made, and we'll share that with those of you who were kind enough to give us your time today, so that you can review this later on and sort of refresh your memory of what was said. And finally, I think that comes just up to 11, yeah, in the UK. So we're going to stop the session there. Thanks everyone again, and looking forward to speaking to you about how we can help you take money out of operating your power systems as soon as you're ready to talk to us. Right, thank you everyone, and have a great day.